Okay. I hope you can hear me. Can you hear me, guys? Can you hear me? Okay. People can hear me. That's okay. Then we can proceed. So what I was saying is that that's why here we are saying we will use the Fourier sine series, Fourier sine, for the representation of the non-homogeneous to satisfy. And I insist you don't need this. You can just look at this function, compute the Fourier coefficients, pre-establish whether it is a full range or a half range. And I gave you a number, and I saw in that number you did in the test, very many actual all of you failed it. You were around 266. I don't know why you failed that number. There was one number of a half range where you are supposed to fill in the values of those functions, but the result was very disappointing. So in this case, once you have this, so from dealing with this, you remember we say that our f of x, this is where you are going to use this f of x here, just the left-hand side, rather the right-hand side. So this is approximately, that function is approximately what? It is a certain n naught over 2, and this is plus the sum of an cos, you still remember this, plus a bn sine. I'm not writing the whole thing. This whole thing is under those brackets. Here we move from n equal to 1 to infinity. I hope you still remember this. The fx here is this 3x. Is that okay? So once you have this, you compute the n naught, you compute the an, there is an here, and you compute the bn. We have 3 Fourier coefficients. That is the n naught, we have the an, and we have the bn. Okay? You look for these 3. Once you look for these 3, you substitute them back and you do the simplification. Substitute them here. You do the simplification. If you do that simplification, you are going to end up with this statement. And this is what we are saying, that the right-hand side of the given differential equation, which is the function 3x, can be represented in a series form of this type here. I guess there is no question there. Okay? So once that is the case, I hope there are no questions here. We have understood how the 3x becomes 6 over pi summation of that. All right. So once this is achieved, then you can go ahead and from this we know now the general form. Remember, on the left-hand side, everything is in y. So the solution of y, you remember where I started this. I told you when you are discussing your differential equations 1, you discuss something called the power, the principle of superposition. When you wanted to get the general solution, you'd have what you call the complementary solution, and you'd look for something called the particular solution, YP. YP, this YP is derived from the non-homogeneous kind of differential equation, which is dependent on the fx given in that equation or system. And the YC is the left-hand side, of that system. So in this case, our right-hand side is this. And remember in here, when you pick the YP would be generalized. I'm hoping what I am saying you still recall. Like in the previous, this very example, I said, if it is 3x, I started by making a remark on some of these. Then we would say, what is our YP? YP doesn't take that form, but YP would take the general form. The general form of YP here would be, since this is linear, we could simply say this is something like alpha x, and you can add something here called a beta, something like that. So we would say the generic form of that YP would be that. And then we would say, okay, since this is second order, we differentiate this one twice, substitute it in there, equate it to this original function 3x, do some comparison of coefficients, and we end up with the value of alpha and beta. It is the same story here, guys. Same exact story. Now, we know that 3x is this. Since 3x is this, we can get the generic solution, the overall generic solution. But what informs that generic solution? It is the nature of the fx here. So since this is the case, this one is y dependent on x, we say the general form of the equation is what I have enclosed in black. Anyone saying no? Contrary to my explanation, the chat room is available. You can forward your contradictions, and then we unpack them together. Silence would mean you have overly understood that indeed yx is represented as this in terms of the generic solution to that system. Good, since there is no question. So we can continue. Now that we know this, we can differentiate this one twice. Remember, we have a y prime prime. So if you differentiate this one twice, remember there is n pi. When you differentiate cos, you'll get n pi. That will give you n pi. Of course, we have the bn. This would be cos n pi x. Okay. Differentiation of a sign gives you a positive cos, and now when you this is the first derivative, by the way. This is y prime. Second derivative, which would be now y prime prime. Differentiating a cos gives you a minus sign, but the n pi still comes out. That is now the minus n squared pi squared. The bn comes back, and this is now sine n pi x. Hopefully there is no one saying no. Why sine Fourier? This guy. I have just explained why sine Fourier, Mr. Kisaki Christopher. Why sine? Okay, that one I have answered. Akisam says no. Okay, maybe someone has already heard why sine. I have told you this one takes the form of the solution, and I'm using your D is one to explain this. This one is already sine. You can see that fx takes that form. So what is the generic form? The generic form is bn sine n pi x. I hope I am clear there. Just like here, the generic form is n naught over 2 an cos bn sine. So if it is a full range, the generic form will be this one here in black. I have said the nature of the solution. The nature of the solution, you get explicit with respect to the function that is given. is indicative of the y. What 3x is approximated to be? I have told you 3x is approximated to be 6 pi summation of that. Remember, we are solving. So if our fx here is approximated to be this, then it means the y value. Remember, you substitute in the values of y to get this one here. If I don't know what is confusing you. If you want to verify that this equation is indeed y prime prime plus 2y is equal to 3x, it means you're going to get a certain y and y that you'll substitute in here, simplify it, and until it gives you 3x. But we are saying 3x is approximated to be 6 over pi summation of that term, implying whatever you are going to substitute in here that will be simplified to give the 3x, which is represented as 6 over pi sum, will be of this form here. I am talking to Kisaki Christopher. So it shouldn't be y the sign. Y the sign is all painted in black and white here. So why the sign? It is the explanation I have just given. Kasirie, rather Kisaki. This is Kisaki Christopher. Akisam Sepuya says no. I don't know. The no of Sepuya is referring to, I don't know whether the comment of Kisaki. Your one no seems hanging, and I can't comment on your one no, Mr. Akisam or Mr. Sepuya. Okay, I think I have answered the why, and in this case now we can proceed. How do we proceed? Okay, I'm going to erase some of this. So I said once you have this, you've differentiated. After differentiating, you can go ahead and substitute these derivatives. That is the y prime prime and the y prime into the left-hand side. So these ones here, I hope you can follow. I have enclosed. They must be substituted into the left-hand side. So these must come there. I hope we are together. So substitute these into the left-hand side and you equate to 3x, but the 3x is 6 pi over that one. And if you do that, and okay, I have to assume fx is 3. No, it is not an assumption, Mr. Kasirie. Indeed, fx is 3x. It is not an assumption. This is a non-homogeneous equation. I'm still talking to Kisaki here. Kisaki, yes, fx is 3x. And because fx is 3x, then what is the approximation of fx in terms of a Fourier series expansion? We are talking of an expansion, a Fourier series expansion. So fx, which is 3x, and initialized at 0 and 1 will give this representation, the one encircled or enclosed in red. And for you to verify this, you must get a certain y that you'll differentiate twice, throw it in here, and you get that one there. So since the Fourier series expansion of 3x is this term here, then it suffices to deduce or to conclude that the y that will be substituted on in the left-hand side would take this form. That is a logical interpretation. Okay, so we can now go ahead. So if you do this, we have differentiated this guy twice, this one here, differentiating it twice, you substitute. I have already explained this. Once you substitute, you equate to this term here. substitute into the equation. This one is being substituted into y prime plus 2y, and this is equal to 3x. So if you substitute into this is the equation we have. Our y is this, differentiated twice gives that, once gives this. The left-hand side, rather the right-hand side of fx is that summation there. What remains is a simplification. If you look at this, you realize that this term here is the same all through. That term there is the same all through, implying that this thing can be simplified. So we can simplify it in terms of sine n pi x. And when we do that simplification, we simply take out the coefficients of these sums, taking that out or collecting terms with respect to sine n pi x. That would give us this statement here. This is what we get. And once you get this, you simplify it by making, rather you make simply Bn the subject. Making Bn the subject gives you this one here. The one I have enclosed in red. Once you get that Bn, but remember, we already have the expression for y, which is 6 pi. So all we need to do in this generic form, please look at what I am encircling, or rather enclosing in the red. This is the generic form. Since this is the generic form, all we need is to substitute the value of Bn, this Bn here. So I am saying that this Bn in green is the whole of the Bn in green the Bn in green is the whole of this statement here. Remember, this is Bn. So Bn will take on that. So our Bn here is the green where it is pointing. I hope I am clear there. So once you substitute Bn back into this, then you have got your final solution as this statement. I hope there are no no's. Okay. All right. I think that is that. There are no questions on that. Since there are no questions, I think I can confidently move on, knowing that with no questions, the problem these people keep saying, clear. Yes, clear, but when I give the tests, it is the reverse. It's like your clear is in the opposite of, say, clear, he goes ahead and we don't burn our data. I appreciate your clearance in this lecture, but this clearance should be exhibited or demonstrated during the test. Clear would imply in my tests you'd be getting 30 out of 30. Unfortunately, that was not the case. Okay, so let's continue. Okay, that is one example. There is another example here now. What does FT? So we have a certain FT. If you look at the FT here, you realize that the FT we have now, if I scroll a little bit. So what is our FT? Our FT T, this is the FT. You can see that one there. So if this is the FT, just look at the range now. FT runs from what? FT runs from -1 to 1. Someone was asking. So now, can we find the representation? This is F -1 to 1. This is a Fourier series expansion. This is full range because it moves from -1 to 1. And you know it is N naught. So the notation is changing a little bit. For us, we write N naught over 2. The N naught over 2, in this case, it is written as C naught. I guess we are together. Then we say the plus you sum from N, we look to 1 to infinity. And this is of N cos. Is that okay? So the N here is what you're writing as the Cn there. The C naught is the N naught. Then we would say plus Bn sine. The Bn in this case is the Dn. I hope no one is getting lost. This is exactly the same formula. Now remember, it is N pi x over L. But since this is in T, our x is actually T. The x now becomes a T. The x is a T. Remember, it is N pi, it is N pi T over L. That's why you can see we have cos N pi T over L sine N pi T over L. And from this, we know the formulas of finding C naught, Cn, and Dn. Please be mindful that the C naught, the Cn, and the Dn, these are the Fourier coefficients we referred to us in the previous lectures as N naught, An, and Bn. I hope I'm clear there. So on doing that, simply substitute. Remember the L is 1. So once you substitute 1 here, this denominator part disappears. That's why now here we write it in the form some of you programmers are very happy with. A programmer always simply takes what they see the very first time. Since some of you could be victims or subscribers to this programming practice, then I think I have clearly indicated that this is indeed that. And from that, we can go ahead using the formula for a full. Remember, the formula is 1 over L integral from minus L to L. This is fx dx. This is simply for your N naught. Or if we write it specific to the example, that is C naught, which is equal to that one. And what we have written here is what we are expressing here. But remember, our ft is 0 from -1 to 0. And it is, was it a 1? I don't remember. I think it is a 1 from 0 to the upper limit L, here being 1. Okay? So once you substitute in here, you get the C naught, which is 1. This helps you get C naught as 1. We have established Cn as 0. And we have got our Dn to be this solution here. I hope there I am clear. Please go back and you do the integration by parts, play with all the different techniques of integration. of the different functions. Once you have that at the fingertips, surely the exams shouldn't become a pain in your, we could say, foot. I don't want to talk like the Americans. So don't let this petty computational dynamics cause unnecessary pain in your foot. Simply, your mastery of the concepts we've discussed with respect to orthogonality and how to determine these Fourier coefficients. When are they half range? When are they full range? Once you have mastered the skill of determining those, then this really should be a very smooth path. Right. Okay, maybe you can clear this off. Okay. So, and once you have this, now we say it takes the form. FT, the solution of FT takes that form. By that form, we're referring to equation 3.9.5. So since we know FT, this is what we are now supposed to differentiate. How many times? Twice. This is going to be differentiated twice. Why twice? It is because of the nature of the equation given. The nature of the equation given is second order x prime prime. This is 2x, which is equal to ft. So why does it take the same form? It takes the same form because if you want to verify this, you'll throw in some value of xt, another value of x prime prime t, simplify the thing for it to give you ft. So it is better you first get to know the representation of ft in a Fourier expansion kind of series term. And then once you succeed in that, the ft can be categorized with respect to its representation in a Fourier series form, and then you simplify the left-hand side of that given equation. Okay, I think that is fine there. So with that said, I can go ahead and we say, since ft was determined as this, we've determined our ft as this part here. We've got ft to be this one here. So since ft takes that form, now we can substitute. We can differentiate and substitute. When you differentiate this one twice, of course, the first derivative, this is a half, the half disappears. You'll get, if you differentiate sine, you'll get n pi cos, okay? For this one here, you'll get n pi cos. And then when you differentiate the second time, again, this is 0. Maybe we do this together. So the first time you differentiate this one, because x is going to take on that form, it will be x prime, which will be what? This will be 2n pi because of this sign here. Remember, this is 0. You bring the 2, so you have 2n pi. And this is over. Since this is x naught, rather 2n pi. Once you have the 2n pi, but remember there is a denominator here of n pi. So this is over n pi. which n pi crosses with that upper n pi. Okay, the 2 is that 2. This is cos n pi t. So when you differentiate this one, that is x dot dot. This will give you a minus n pi because of that, and this will be sine of n pi t. So if you do that, it means basically you're going to only have this term and you have that term. These are halves will disappear. That's why you see that when you substitute back into our formula, we are going to substitute this into this term here. I hope we are together how the substitution is being done. Okay, so if you substitute back, what do you get? If you substitute this into that, remember the first term, which is n naught over. It is n naught, and we had already got our n naught. We substitute it there. Then for the next part of the sum, we have already done this together. First derivative, I think I made this one close to that one, then I got that. We need to check out this because I see there are some squares here. Maybe I messed up somewhere. I may have messed up when we took the general form of our expression. The general form, that is substituting x t into 9.4 into the ordinary differentiation 3.1. I hope I'm not making a mistake a little bit up here, or maybe I omitted a step. That one is also an issue of concern. Okay. Okay. Andrew. Hey. Okay. Okay. So what I was saying is from this, we have this. Once we substitute our x naught, we have ft. Ft is this, it is given by that, but the x, this is x prime prime. We differentiated this one twice. The first derivative n part went with that one, then the second derivative. Okay. No. I made the wrong substitution here. Okay, I've seen the mistake I made. The mistake I made is I took my solution to be this one. My solution is not, the mistake I made was to take this one as the form. I had substituted this to be xt. But remember, this one has already got its representation. I think this is what we have. Yes. So this is my, this is ft. If this is ft, we have x prime prime. Is that okay? So the generic form, okay, I think I've noticed where the mistake is. The mistake is in the generic form that I considered. Our generic form should be this one. Is that okay? It should be n naught plus the summation of bn sine n pi t. That's why I was making the mistake. I don't know what this one is saying, but I think we differentiate xt. This is no whatever. What do you mean we differentiate xt? We are differentiating with respect to t. Okay, what I'm trying to say that since ft, we have got the, after substituting c naught, cn, and dn. Is that okay? After having that form of substitution, we have got the representation of x. Now we need to substitute. And if this is it, then the generic form, these are half, we can give it just an n naught. Then this one here, we call it bn. So you have a general statement where we say our x is n naught. This is plus the summation, and this is bn. This is sine n pi t, n pi t. This is the general form, guys. So we have this as the general form, implying that if you differentiate this one once, differentiating this one once with respect to t, definitely the n naught is not there, it will disappear. What you will have is just this term here. So this will be the bn, not even bn, we have n naught, an, and that I have to add here. This is, this is, I need to edit this a little bit, guys, a little bit, eraser. This is an. The general form is sum. This is a n cos n pi t plus bn sine n pi t. Then we enclose off this and we enclose off that. That is going to be the general form. Remember, we got the expression for C naught, which was 1, Cn, which was 0, and Dn, which is this one here. So you differentiate this one twice. If you differentiate this twice, N naught is 0 here, plus this one here, when you differentiate it, is going to give you N pi. This is going to give you N pi sine n pi t. I hope I'm with you guys. But remember, there is a certain n here with a negative. Eraser, I'll remove this one and the equal signs. I come back here. This is a certain x, which is equal to negative a n. So this is a negative an because cos will give you a negative, and then this is a plus. Then you bring this one. This is n pi. This is b n cos n pi t. I hope I'm clear there. That is x. Then you look for x prime prime. This session is running out. You log back in. X prime prime, you are going to differentiate this term here. And once you differentiate this, you are going to get the n squared, n pi squared. And you'll get that 2 minus n pi squared with the n, the n naught, the bn. This session is running out. Please log back in. Just log back in. Sentongo, you can raise your issue in the chat and I answer it and we go away. So just log back in, guys, log back in. We are going to differentiate this twice. I'm not going to rewrite this. This will be n squared pi squared, and it will now be a negative. And then this one will be n squared pi squared b